So it says an engineer needs a metal box to shield sensitive electronic devices from external electric fields. One side of the box should be open so that it can be placed over the components. So this is just the same situation we've been dealing with. Okay, so you're going to draw your little corners in and figure out what you need to do. So the box can be made from a 3 meter by 4 meter sheet of metal by cutting squares from the corners and folding at the sides. So let's start by drawing a little picture and thinking about what this probably looks like. Okay, so we are told that it is a 3 by 4 meter. We're kind of just sketching it out. So let's say 3 by 4 meters, and then I have a little square in each of the corners. And when they say square, that's giving me information that both of these will be like my unknown values. Okay, so did y'all make it that far? All right, so give a function that models the volume of the metal box and give a reasonable domain in context to the problem. All right, so let's do that. This is really important. So I have volume based on x, and then I'm going to have, I might as well just, I was going to just write it there, but I'll put the domain there as well. Okay, so I have length times width times height, right? So I need 3 dimensions being multiplied. What is going to be this distance here? Let's just call it length, 4 minus 2x. So I have 4 minus 2x, and then what is this little length here? 3 minus 2x. And then I need one side, cut the corners out and fold up the little flaps. I need the height. What is the height going to be? Just x. Okay, so that's the function that will give us volume. And now I need the domain. So the first x here, there's nothing to really solve for, but x must be greater than 0, correct? So this will be the domain. Then I take the 4 minus 2x and basically say that it also has to be greater than 0, and the 3 minus 2x and say that it also has to be greater than 0. So when I solve for this one, x must be what? Less than 2. Okay, so 4 minus 4 would equal 0, and that would not work. So it's got to be something less than 2. So like 1 would work. 4 minus 2 would give me 2 for that dimension. That'd be fine. This one's going to be what? X must be what? Less than. Do y'all know what I'm doing here? I'm just solving. So I basically say 3 minus 2x, and then I would move the 2x over by adding, I would divide by 2, divide by 2. So x would have to be less than 3 halves. So 3 halves. Yes, Haley? No, you don't have to show all the work. I was doing that because I don't feel like everybody's really getting it, so I was showing everyone. Some of y'all could jump straight to saying, oh, x has to be less than 2, because a 2 will not work, because 4 minus 4 is going to give you a 0, so it has to be something smaller than a 2. So which one of these is more restrictive? The second one, right? So my domain is going to be 0 and then 3 halves, or you could do 1.5, either one's fine. So this is my domain there. So how is that?
And so the domain's never like in brackets on these problems?
No, the domain will not have brackets. It's going to be parentheses because it has to be greater than 0 and then less than some other value for x. Okay? So then it wants to know the maximum volume of the box. So I'm just going to take this volume function and plug it into my calculator, and then I'm going to find the maximum. So I think Haley asked that question earlier. How do you know when you're looking for the maximum versus the x-intercepts? This is your clue that you're looking for the maximum. So let's go to our calculator and let's plug that in and see what we get. Okay, so it's going to be x, and then it was 4 minus 2x. I'm going to kind of just change this up. And then it was 3 minus 2x, right? Okay, so let's see if our window is reasonable. And what are we modeling here? We're modeling volume, so it could get a little bit bigger, so I may just leave it like that just to kind of see what's happening here. Okay, so this is a polynomial with a degree of what? 3. So the graph makes sense. It has, basically it looks like it has what here? Even multiplicity, maybe. We'll look at that, okay? But where is the maximum that we can use for this problem? Is it right here? Yeah, it's right here. Even though it goes to infinity, that's not really a maximum we're going to be able to locate, obviously. So we're going to find the maximum for this little piece of the curve there, okay? So I may change my window just a little bit because I'm more interested in closer to the true max. So it's going to be an x in here. So it looks like it's right about there between 0 and 1, I guess. So second, calculate, I'm going to find what? A maximum. And this is like, you know, older material. We did this last part of the unit. So press enter, travel to the right of it. Don't go too far. I went too far. So go back. Somewhere along here is where you want to go. And then press enter and press enter. So it's kind of weird, but 0.566 is going to be the answer to that one. So 0.566 is going to maximize the volume. Are y'all with me on that? So x equal to 0.566 will maximize the volume. But what dimensions of the box will result in this maximum volume? So what was the maximum volume, first of all? No, it's just 3.03. So it's not a very big box, is it? Okay. Does anybody remember if that's what the answer key said?
Yes.
Okay. So it just feels kind of weird because the numbers are kind of small, but it's probably just because we made up the problem and just kind of worked out that way. So this I don't really need for the answer. I need this, and then I have to plug in the other, plug it into the other equation. So I'm going to have an x of 0.566 by, and then I'm just going to do what? 4 times. So you could just do this in your calculator. So 4 minus 2 times 0.566, and that gives me what? 2.87? 2.87-ish times, and then we'll do 3 minus 2 times 0.566. So do y'all understand what I'm doing here? And then I get 1.868. And these are going to be in meters. So these are all in meters here, guys. Okay, so does that make sense for that one? Now that one we didn't solve for anything, so I really want to do one where we have to solve for something. So I would say, let me just take a quick glance. 17 and 18 are both problems you definitely want to be able to do. Okay, you want to be able to know how to do. So y'all worked on which one would you prefer I work on first? 17. Okay. So an open box is made from a square piece of material. So we know we're starting with a square. That doesn't look much like a square, but it is. Okay, and then 36 centimeters on each side. By cutting equal squares with sides of length x, if I could talk, we're going to fold up the corners and make a box. If the volume of the box is to be greater than 2,700 cubic centimeters, what are the possible heights of the box? So this is a perfect one for us to do. All right, so first start by writing out the volume function. So volume based on x, or as a function of x, will be equal to what? So I need this. What is this length? 36 minus 2x. And then the other length is exactly the same, right? So this will just be squared. And then I have my height when I fold up the box is going to be x out front. So there's my volume function. Is everybody good with that? And then we want to solve for this if the volume of the box is to be greater than 2,700. So basically I'm going to say x times 36 minus 2x all squared must be greater than or equal to what? Oh, greater than, sorry. So 2,700. Okay? Now let's go back to the volume function and let's talk about our domain. Let's find our domain from right here. So we know x must be greater than 0, and then when I solve this one, x must be less than what? It'd just be 36 divided by 2, right? Okay, is everybody seeing that piece of it? So x would have to be less than what? 18. Because if x is equal to 18, I get 0, and that's not going to work. I'm going to get a volume of 0, and that's not, there's no function if you have no volume. There's no box if you have no volume. So my domain is going to be 0, 18. I'll get my solution and kind of overlay that domain on top, if that makes any sense. So now we need to go to the calculator, and we need to solve this, and all I'm going to do is subtract 2,700 over, so then that will be greater than 0. So this is what I'm going to graph in the calculator. So go do that. So I have x and then 36 minus 2x all squared. And then I subtract what? What did I subtract? Yeah, it's 2,700. And then I'm going to graph it now. This is probably not going to work for me because my window, I haven't really done much with it. Okay, so I can see that I have a couple of intercepts here. Okay. So I need to find those and sort of figure out where is it above or where is it below the x-axis. Okay, so find those. Do you know how to do this? Okay, so it's going to be second calc. Now, before I do that, what do you think this one is? 3. If you think it's a 3, then you could just go to the data table and yeah, for sure it is a 3. Okay, now these negatives won't help me anyway, so the other one's not here, so I'm going to have to find it. So second calc, and I'm going to find the 0. And I'm going to say that like 5 is a good left bound and 10 is a good right bound. And then guess. So I have 9.626. Okay, so let's go do a sign chart. So here's my sign chart. So I had a 3, right? And I had a what? 9.626. Now, do I possibly have any more roots, or is that it? Do I have one at 0? Okay, but this is y'all, this is really important. Once you subtract that 2,700, what would have been roots at 0 and at 18 got what? They got shifted down by 2,700. So it's shifted down. So these are no longer going to give us our x-intercepts or our roots because it's different. It's been shifted down. Okay? So I think something else is going on. So let's go back to the calculator and kind of look at it. Maybe I'll change my window and I don't know. Have y'all played around with this? So what is going on? It's got to be going up, down, and it's got to be coming back up again. But will that even matter?
Probably not.
Well, probably not, you're right, because what do we have here? Our domain is in this region right here, right? Okay, so let's see. I'm just not happy with this. Let's do -50. I'll change that. For the x or for the y? For the x? Okay. This might work too, but probably not. It may be. Okay, so what's going on here? I do have another root over here. So you know, even though you can't really tell, it looks like they're just going straight up and down. What is the behavior of this graph? You know it's coming up from the left and then going down and then back up. How do I know that? Because it's a degree of 3 with a positive Lie coefficient. So this value we need to do second, calculate 0, and let's see where we are. In a minute I'll be coming up. Oops, I went too fast. Now, I'm pressing the right key and I can see it. So when I press the left key, I know I'm to the left of it. Press enter. Go to the right of it. Press enter. Press enter. And it's 23.37. So 23.37 is our other one way over here. 23.37. And then what are our signs? We can either do it from just our knowledge of the graph. So what do I put here, negative or positive? Negative. Could I take like a 0 and plug it in? Yeah, absolutely, and see what I get. But I really don't have to because I know my graph is kind of doing this, like this, like that, okay? So then I have a positive, and I have a negative, and then I have a positive. What am I looking for here, negatives or positives? Yes, I'm looking for my positives. Okay, only, not equal to 0 and not negative. So I'm looking for this region in here. So it'd be 3, 9.626. And first I'll write my solution as it really would be. So this would be what? Parenthesis, in union with what? 23.37, comma, infinity. Now, my domain was 0 to 18. So guess what? This whole piece of it is not even going to work for us. So this is my solution right there. So 3, 9.626. Okay, let's just kind of look at that. Way on down here. So it's right there. Okay, what about 18? How's that going for you? Okay, 18's fine. Okay, so why don't y'all just like keep checking your answers, that kind of thing. I can put out the key. Are there any from the earlier sections you need to see? Okay, sure.
One of the rational roots ones, I missed that.
One of the rational, like pick a problem and tell me.
6, 7, or 8.
6, 7, or 8. Okay, now 6, 7, or 8. So let's do number 6 because it's just a basic one. When we're finding all the possible rational roots, we do all of our factors of P over all our factors of Q. So this would be plus and minus. And factors of 6 are 1, 2, 3, and 6. Factors of 5 are just 1 and 5. And I need to pair them. I cannot just leave them like this. Is everybody paying attention? I can't just leave it like that. So I need to do 1 with 1, 1 with 5. 2 with 1, 2 with 5. 3 with 1, 3 with 5. 6 with 1, 6 with 5. And none of these happen to repeat or duplicate, so it's all of them. And that's how you find all your possible rational roots. And we talked about this. Really all you're doing is listing them so that when you graph it in your calculator, you can do what? You can use synthetic division. You can identify the one that you can use in synthetic division. So I'm going to say this. If it is not in your list of possible rational roots, but you see it on the calculator like as an x-intercept, you can't just write down that x-intercept. And Jack, this is kind of to answer your question. You can't just write down that x-intercept. You have to use one of those that you find, do your synthetic simplification down to a quadratic, and then get those irrationals from the quadratic formula or from square roots. Does that make sense? So really that's all you're doing with this. It's a little tool that you have to figure out which one of your x-intercepts are real rationals, because those are the ones you use in the synthetic division. For these, like I would probably see if I can factor, and I think this does factor. So that'd be x squared and then x plus 6, and then here would be plus 4 and then x plus 6. So this is going to be x squared plus 4. I'm going to get 2 imaginaries from that, and then x plus 6. So my roots here are going to be a -6, and then I'm going to have plus and minus 2i. So those would be my roots there. 8 is the one where you would take your 1 plus 2i, and you would also set it up with 1 minus 2i, and you would use synthetic division, and whatever you get from here would be a quadratic. Then you can go and find the other 2 roots. Whatever nature they are, you would find the other 2 roots that way. This you just have to be really careful with them, you know, just multiplying and adding and subtracting complex numbers. Kind of gets tricky there. Do not forget your higher power, like higher degree factoring techniques. I'll kind of give you one of those. Really, everything on the review is good for you to know how to do. And notice that this whole top part is no calculator, and that's the part you will not have a calculator on. I don't really see one. What I'm talking about, though, is make sure, like, x to the 6 plus 3x cubed plus 2. Would you know how to factor that? You remember those?
Yes.
It'd be x cubed plus 2 times x cubed plus 1. Very good. And then a lot of times you could go on and factor those some more. So make sure you know how to do those. And I literally just made that one up. So other questions? Y'all just kind of spout them out and I'll do them. Yes.
Are we like questions on the test with you, like the SOAP formula kind of thing?
Yes, you do need to remember that. Y'all remember how to do differences
Yeah.
and sums of 2 perfect cubes? Okay. Does anybody need me to show you? Huh? Yes, sure. I'll make up one. Y'all may want to write this down.
Well, yeah, there's one on the first page.
Okay, awesome. Thank you. Yes, you're right. Here we go. So my base here is what?
4x.
Very good. 4x is being cubed, and then here 1 is being cubed. So it's going to be binomial, trinomial. So 4x, and then I'm going to use same and the 1. So I'm using my bases, so I'll put those in place. So then I square 4x here, so 16x squared, and then a 1 goes there. And then I simply multiply the 2 bases and get 4x there. So same is negative, opposite, and always positive. And then this will always result in something that you have to put into the quadratic formula if you're asked for the actual roots. This, of course, would just be 1/4. Okay, any more of the factoring ones you need to see? So remember, grouping is a technique you may need to use. If it's a higher ordered polynomial, you just factor it like you normally would. Just remember, like, x to the 6 is really x cubed times x cubed, that kind of thing. How did this whole section right here go? Because this is sort of conceptual in nature, this whole section here. Any questions on that, or y'all need to see the answer? You see the answers? Okay. Well, it's way on up here, sorry. Okay. Tell whether each statement is true or false. A is x plus 1 and B is x squared minus 2x minus 3. If P of 1 is equal to 0, this is false. There's a trick there. They're basically saying you better know that if x plus 1 is a factor, then -1 would give you a 0. Not 1, but -1 would give you a 0. So B is like the correction to A. A is false, B is true. So that's kind of what's going on with those two. Synthetic substitution can be used to determine if A is a factor of B. Absolutely. You're looking for a remainder of 0. And if you get a remainder of 0, then R is a root and x minus R is a factor. Okay. I've only had one person take the test already.
Did it fail?
No, perfect score. I haven't tell you who that was, but
Kayla.
it took them 30 minutes to do it too. So we shortened it quite a bit. So
I feel like the work problem
Oh,
is
yeah,
super
it was
hard.
no, there's only a few, and if you know and understand these down here, like 16, 17, and 18, just make sure you understand those. Watch the video from last night. Well, I put it yesterday's date, but it was for y'all to watch last night on finding the domain and kind of how the domain is used. But basically, find your solution, your intervals just like normal, and then sort of think about laying the domain on top of it, and you have to cut it off where it's not valid.
Wait, so for number 17 again, so,
For number 17 here,
why is it just between 3 and 9.6 and doesn't go to 23? Because,
okay, it's because the other interval, whatever, was it 23 point what? I can't remember.
0.37.
23.37, and it was to infinity. What's going on here is our domain we had determined was this, right? So it's the fact that it's not in the domain. So I cannot use algebraically, yes, it's a solution. It's the x's that give you y's that are positive for that function. But it's not in our domain in context of the problem. So that's what's going on here. So this would be our domain. All right. And then y'all all get that once you write your volume function, y'all look at B down here. This is the function for volume. Are y'all with me? And then I use that function and set it equal or less than, greater than, whatever I'm trying to achieve to the volume that I'm interested in. So the function for volume is actually this first, and then I set it equal to and then subtract over that value and figure out what I'm dealing with. When you subtract it over, if you're looking for less than, greater than, whatever, 0, it's exactly what we did on the worksheet that we were working on for a couple days, those worksheets. All right, so any others? How about the table? What do y'all remember about the table? The basic takeaway was the degree of a polynomial will give you the maximum number of real zeros, but then the extrema are always going to be, when you sum them up, they're always going to be what?
One less than the degree.
One less than the degree of the polynomial, okay? So if you're given a problem like that, you could sketch it out and just kind of see what you have, just like we did. I think y'all are going to do great. So I'll take up the review tomorrow, so just make sure you have it all finished and everything.